today we're covering containers, not Docker containers. Wait, if we're not covering Docker containers, then how are we covering containers? We're covering SystemD Namespace containers. This is a container format and a container runtime that's included with nearly every Linux distribution that runs systemd. And right now, that's a lot of them. Most people don't know about them. Most people don't know that they exist and that they have the capability of running them. We're going to get into the history behind systemd namespace containers, what brought them to fruition, some of the things that they replaced, how they fit in the ecosystem. Why would you run a systemd namespace container over a Docker container? Systemd namespace containers were influenced in many ways by Docker containers, but they serve really somewhat different purposes, although there's spaces where you can use them in some similar scenarios. Lastly, we're going to pull up an actual environment and we're going to build a systemd namespace container. We're going to use Ansible to help with our deployment, and all of that scripting and utilities will be stored in our Git repository. From here on, we're going to continue to put more content on GitHub anytime we're doing software development, anytime we're doing scripting. It's all going to end up on the GitHub page. That'll allow you to pull it down and attempt to duplicate it. And if you run into any issues, let me know. We'll see if we can get it worked out. So systemd namespace containers. Why are these interesting? Why have they been created? Well, in order to talk about systemd namespace containers, we got to take a little bit of a step back and talk a little bit about Docker containers. The team that created Docker containers originally had a web hosting style company that they were building. And one of the things that they were using was a different container format, something called LXCs, or Linux containers. And what they found is that managing Linux containers at scale was becoming quite troublesome, that there wasn't a lot of tooling around it. And while these Linux containers were functional, it was just quite difficult for them to be able to manage a large number of these various different types of them. They were just continuing to build custom bespoke tooling around LXCs. Around this same time, BSD also has BSD jails, and then a long time component of Linux, chroots, have also existed. Chroots standing for change roots. Change roots are somewhat similar to Linux containers in that they're file system based. If you go back further in the Linux and Unix days, there's this concept around everything being a file. And what this concept means is that almost everything in the operating system is either an actual file or a file inode. So an example of a file inode is inside of Linux you have a directory for proc, and that directory has inodes that map to hardware devices. So you might have something that maps to USB, you might have something that maps to your PCI Express, you might have something that maps to all of your hardware interfaces, but from a operating system perspective, they look like files. Some of these inodes, you can read from them, you can write to them. And if you think of this phrase called input-output devices from a Linux operating system perspective, that's how it looks at these input-output devices. So if we take this everything as a file concept a step further, you may have heard about operating system compatibility. In the Linux world, an example of operating system compatibility is this phrase called POSIX. I'll put the acronym down here. So a POSIX Linux device plus everything being a file means that all you need is the appropriate file structure with the appropriate set of files, and technically speaking, you have Linux. So if you launch a service or an application, a binary, in speaking, inside the right directory with relative to something that looks like a Linux file system, it'll look to and read from other relative files that it needs, and it'll start running. So that's the kind of concept of a chroot. So if you set up different structures of your directory to match an appropriate Linux directory, then you can have a chroot. And so I've been in environments where we've managed chroots, had different install files, built out different operating systems, and then you can run files from them. And they, again, look relative to what appears to be the root directory, even though they're not actually the root directory. So you've got things like Linux containers, you've got the challenges of managing them, the lack of tooling, every time you want, whether it's an LXC image or a chroot, you essentially have to build that from scratch. You have to use things like rsync maybe to generate a file tree somewhere that you can sync down and have the appropriate structure that it needs to look like in order to run those environments. So this is kind of complex. Every team I've seen use these type of technologies wrote their own in-house custom stuff to deal with it. There's always edge cases, bugs, issues that needed to be worked out. And so in order to do these things, it's also not for the faint of heart, right? The skill bar is kind of high. And then just because the skill bar is so high just to get a nice environment you run in, that's totally separate from trying to then scale these out and build a custom one with this application, a custom one with that application. And so that's really where the tooling around SystemD, so that's really where the tooling around Docker containers really shines. Wait, I thought we were talking about SystemD namespace containers. We keep talking about Docker. Well, we're getting there. So we talked about files, everything being a file, operating system compatibility with POSIX. We talked about things being hard to manage. We talked about Docker really opening up the industry's mind around what it meant to be able to manage these things. Well, chroots were a pretty common structure that could be used in a Linux operating system. However, when SystemD became pretty common standard around all of the major distributions, it's a major process runner for Arch Linux. It's a major process runner for CentOS. It's the major process runner for Debian. It later then overtook Upstart and became the major process runner for Ubuntu. Well, if we look at those distributions, I mean, those distributions dominate the landscape of enterprise server Linux distributions, even home Linux distributions. SUSE is also a big one out there. So one of the things that SystemD did is it changed the init system from something called SysV or Sys5, and those Sys5 managed different things called run levels, and all of these things were managed by, drumroll, files. Remember, everything used to be a file. In this case, now we've moved into SystemD, and in the SystemD world, we have a lot more daemons. That's what the D stands for, the system daemon. And the system daemon comes with a lot of other friends, other daemons, an example being like the journal D, the journal daemon, or the logging daemon. And so you end up having all of these running services now that make up your Linux distribution. And so now launching an executable with the appropriate file structure is not enough to fully run a chroot, for example. Now if you're running a binary and you wanted to leverage this chroot functionality, and that chroot now makes a system call that leverages a running daemon, well, if you're just relative in a file path, there is no new running daemon for you. So how does this work? And generally speaking, it doesn't. If you happen to use a very specific type of binary that happens not to call anything that relies on SystemD, then you could get away with it. But generally speaking, it doesn't work. You know, if you want to do something as small as in this environment, change the password. Well, it turns out that calls something that hits the running daemon managed by SystemD. So many things before you realize it, they all roll back to SystemD. So what does that mean? That means in this new world of SystemD, chroots essentially don't function very well if you want to use them specifically to run binaries and applications out of them. So they had to replace it with something. And so they learned a lot from Docker and some of the things that they saw. So they said, hey, we can try this SystemD namespace container. And what that can do is give you a simple chroot-like functionality, simple shell-like functionality, or we can even allow you to boot into that environment, giving you your entire set of SystemD utilities in order to manage that separate service. And we can be smart enough behind the scenes to figure out what is appropriate or not appropriate to share with this new environment in your main host. And so they took a lot of concepts around what would be a privileged or unprivileged container. So that's how we got here. Chroots are broken. SystemD, no longer in most Linux distributions, is everything a file, right? We have daemons that run things. So you need a new service that allows you to be able to run these separate binaries as daemons. We need a separate service that allows you to run these binaries so that they can call the relative daemons that they need in order to run. SystemD nspawn, that's the service that does it. Another tool that came along with that in most of these distributions is a tool also called machine control. All right, let's actually jump into using these SystemD Namespace containers. All right, so what I'm going to do here is pull down the Ansible playbook that I have written up to take care of creating this SystemD Namespace container from scratch. So I'm going to try to run it. And one of the first things you'll see here is that I don't have sudo privileges. So this is a good time to point to software that I'm running in the environment. I have that linked above, because I'm going to have to go into my free IPA server and use the policy component that I mentioned in the past in order to give myself sudo privileges. And every machine I have joined to this IPA controller just got that policy for my account. So all of them now, when I log into them, will have this exact same policy applied. This is slightly different than using Ansible to edit the etc sudoers file and say push out a new configuration. I'm pushing out a new configuration slightly different. The con in this approach is that it's baked into the centralized management tool. So rolling back from a historical perspective is not quite the same as, say, managing this configuration with Ansible and Git in sort of a GitOps style. So we want to also take a quick look at the playbook itself. And you'll see that it's a pretty straightforward playbook. It has a number of phases, and let's talk about what this does while we kick this off. So what you see here is that it's saying we're going to bootstrap a directory, and we're going to bootstrap this directory by installing a number of files into it. And we're going to install the files into this directory the exact same way you would install files into a new operating system. So let's say when you boot a new machine in Linux and you're in, say, Pixie Boot, for example, a script could say, hey, I want you to look at these yum repositories, and I want you to install these files into this file system, starting with the root directory of this machine. And when you're all done, I'll reboot and I'll run off of the files you put here. So we're following sort of the same mindset. Instead of, we're not going to install these files down into the root directory, we're going to install them into this directory that I declare. And so we're essentially building a directory with all of the capabilities or all of the packages that it would need on there. So you'll notice we start with RPM first, and then we go to yum. This is you need RPM before you can use yum. So in the Ansible, you see a little warning around, hey, we saw you use the RPM command, why don't you just use yum? Because in the directory area where we're working with, there is no yum yet. So we need to use RPM to be able to get a base install that includes yum. Then once we do yum, then we can point yum to a directory. And you see that in the Ansible script as a flag on yum that, hey, we're going to actually use this with a directory. Then from there, we do an infrastructure server install. This step takes a little bit of time, so we're going to jump ahead in time here. But once you're done, we'll have a mini Linux environment. The biggest thing to know here is that if you're going to bootstrap an environment, it has to use the same package manager as the operating system you're using. However, if you want to use what we're going to do next, which is a built image, you can use a built image from a different distribution. Another thing to note is, and this is where we start to talk about how tooling can get complex and why Docker is so awesome. Technically, you could then take this directory for the CentOS machine and you can put it on the file server. And you can have a Ubuntu machine, a Debian machine, other machines, pull down that file system that is an infrastructure server base install, that as a tarball as an example, and each one of them can then use that to generate images and run containers, SystemD Namespace containers, off of that base image that you created. But now you have to have the tooling of bootstrapping the environment, this clunky bootstrap, building it all up, and then tarring the directory, putting it on the web server, and then pulling it back down. So another utility you'll see in a little bit is called machine control. And machine control is the utility that could pull images down remotely and run them if they're packaged in an appropriate way. So once you have everything down and available, now you can use the systemd nspawn command. And what this is going to allow you to do is to run that environment. So you have two ways of using this environment. You can boot into it, or you can just get a shell into it. Now, understand, when you just get a shell into an environment, it's not fully functional. This goes back to what I was saying earlier around certain commands needing daemons to be running in order to have access to them. So the -b flag allows you to boot that invite in that environment and init it with systemd. Now this is something that is quite a bit different than the Docker environment. In the Docker environment, you don't really want to use systemd for anything, and Docker sort of gets around. So in this example, you can run the systemd command with or without the boot flag, the -b, and that determines whether or not you're getting a shell or you're going to get a full systemd environment. So what you saw is I ran -b for boot and then -D for directory, and I passed it the directory where I initialized that entire CentOS 7 environment, and then I booted that whole thing. And then what you saw is an actual initialization process you would see from any normal systemd based operating system, and boom, I got a shell. Part of that systemd unit, I actually put a password in a shadow file, so it was already, part of the install. It's part of the instructions, basic password, change, 1, 2, 3, 4, just to get things running. So that's the basic root password for this environment. And then from there, you can log right in. To get out of this shell, you have to hit Control close bracket 3 times. So Control close, close, close. Okay, so we bootstrapped an environment from just nothing, created an entire environment, and then booted into it. Now let's take an established image. So in this case, we're gonna go to Ubuntu because we're on a CentOS-based operating system. Let's go to a Ubuntu prepackaged image. Let's get one of their daily images that they produce every day based on their current, one of their long-term stable images. This one's gonna be based on Bionic. And as you see when I log into, we have AMD 64 images, we have ARM images, and different types of images. They have VirtualBox images sitting here. They have a number of images. So if you're not aware, you can come into this thing and get things moving pretty quickly. So this is sort of what they call their cloud images environment. So they've got a bunch of images already ready to bootstrap and initialize that process. We're going to use the machine control pull raw. It's going to pull it directly from the Ubuntu servers and then put that image in the machine control environment so that you can run off of it. Once we have that image stored within machine control, then we could say, hey, systemd nspawn, go ahead and run this environment. Now, some things worth noting, and I'm going to show a little bit of this. Machine control is supposed to also be able to start, stop, run images, etc. I found, at least in the CentOS version, that A, some of the machine control commands that are in this documentation don't exist, and B, I've never gotten anything to boot with machine control from a CentOS image. However, systemd namespace does that. So even though I've never got machine control to work, I haven't needed it to, because I can just run it from systemd namespace or nspawn. What I do is I just make a systemd unit for the systemd nspawn command, and then you get all those services. You can then enable it. You can say what you need it to start after. You can stop it. You can run status on it. And so that's how I've run these things. Okay, so now that we've found the image that we're going to pull, let's go ahead and pull it down. So now that you've seen that it's been downloaded to the device, you can see machine control, and we can show that image that's here. And now that it's here, we can run that systemd nspawn command again. And so you can run it again with -m. So this time we're not using -capital. So you can run systemd nspawn with -M. So this is different than -capital D. -capital D pointed you to a directory. -M points you to a machine. Once you point to the machine image that we have here, then we can actually just run the environment. From there, you have an option of, again, running the shell or booting the environment. So the first thing we're going to do is run the shell so that we get right into a shell with root privileges, and then we can set the password so that we know what it is. Then once we set the root password, then we can go back and run systemd nspawn -b cap m. So the last time it was -b cap d for directory. This time it's -b for boot, and then -cap m for machine. And now when we boot, we'll boot and we'll know what our password is, and we can now log in. This time I set the password to be the same thing, 1234, so we can just hop right in. Getting out, now we're in the same exact kind of environment. So getting out is the same, control bracket, bracket, bracket. But notice, we're not in a CentOS environment anymore. We're in a Ubuntu environment. And so now we've taken and used SystemD Namespace to build two different types of containers. So that's pretty cool. When I built the environment from the image and just did an initial startup with namespace, I noticed that I didn't have any name servers available. So I was able to set the name servers to my local DNS servers, and from there I was able to, with using this machine image, actually get to the network once I had a DNS server. I don't have time to get into it here, but just know that there's lots of different advanced networking configurations you can do here. So you have a lot of control over how you want to do some of the networking things. Just know that there are configuration parameters available to you, even though we don't go into them here. One thing to know, especially this is more so for the machine control side, is I found again with the CentOS distribution, it's particular to CentOS 7, it may have been updated in CentOS 8. I haven't checked yet. I've seen very limited amount of the machine control functionality actually working, so I've always just used the SystemD Namespace capabilities. And then something else I found interesting, I just happened to look at another service orchestrator that is kind of like Kubernetes but isn't purely focused on running containers. That's focused on running services across a cluster, and that's called Nomad from HashiCorp. And so I was wondering, did they, in the past I saw they had capabilities for Linux containers, and I just took a peek, and I happened to see that the community now supports SystemD Namespace containers. Not surprised, just because of the way Nomad works, allowing you to run execing processes, to be able to run Java artifacts, to run Docker containers with different runtimes, containerd natively. It only made sense for it to be able to orchestrate names and spawn containers. And so also part of that is just like being able to pull a Docker image. If you had hosted images that you were running, for example, I talked about bootstrapping your directory, tarring that up and putting that on the web server. Nomad could then pull that image down and run it with the appropriate configuration. So you could start to leverage things like Nomad to give yourself an orchestration layer. Now, would you really want to do that? There's probably some use cases. One thing worth referencing is why you might want to use an Ansible container. So Docker, in my opinion, has just a lot of tools that would make it compelling a majority of the time. However, one thing to know is Docker is very opinionated about what you should or should not put in the Docker container. And most of that is for good reason. One of the things, and you'll start to see this theme on the channel, is you want to understand why a rule of thumb is created and when a rule of thumb doesn't apply. Opinionated is generally good because it takes the 98, 99, maybe 95, a majority of the cases, and it boils them down and says, hey, if you follow these rules, you will be good to go in most cases. When you really start to dig in, though, not everything falls into one of those happy path, great scenarios. It just doesn't. So when that happens, what do? You either struggle and fight with it, or you have to have a different level of mastery with the technology to understand when you can sort of tweak it and use it even though they're saying don't do that, or know when you're just not using the right tool for the job. So in my case, I like the concept of immutable changes on an operating system. So immutable is a buzzword right now, especially because of blockchain and things like that. However, the main thing to know is you want to be able to make a change and unmake that change and be at the exact same state. And typically speaking, when you're dealing with operating systems, when you're dealing with servers, bare metal, you don't have that ability. You could do this with VMs, right? You could take a snapshot, make a change. You don't like the change, you can roll it back. Some services aren't the best suited for VMs. Some services definitely aren't best suited for Docker containers. If you are trying to do something and you're a little bit resource constrained, you may have to dedicate a bit more resources to a VM than you may really want. right? And if you dedicate that down into something much more lightweight, like a namespace container, it's just going to use a lot less resources. So in my case, I've mentioned this FreeIPA. I don't run FreeIPA in a VM, but I don't run it bare metal. And FreeIPA is not a good candidate because of how it installs, what it requires for Docker. So I happen to run that in a SystemD namespace container. Speaking of running FreeIPA happily from an nspawn container, here's a quick example of the systemd unit. This is literally the systemd unit that I'm running my production FreeIPA with. Notice that you can point to the different targets that you need to rely on. Notice I'm calling out the -boot flag. I'm also calling out the directory flag and the machine and labeling it. So when this is running, if you did machine control list, you would see the word FreeIPA there because I gave it a easy label for machine control. But this just gives me a service that I can then say, hey, enable this service, start it at runtime, monitor it. And now it has an entire tree of systemd to also monitor the things that are running under it, right? And this is a little bit of inception, right? We have the systemd of the host, launching systemd of this environment, this CentOS environment, and then that systemd has systemd units for the different components of FreeIPA. So FreeIPA has 3 or 4 different things that it's running, and its systemd unit is managing those. Now remember when I said not well suited, right? In Docker, you don't really, the rule of thumb is you're not using systemd to invoke your services, right? You want to invoke those services in a different way and not require the process manager or systemd to be the thing that starts your stuff. So it's not a fit there. But here it works just fine. Systemd starts up this environment and another systemd manages the application. And when in production, you'll find there's a number of applications that are built this way, and maybe eventually they'll get migrated over to be able to run in a more orchestrated, containerized environment. But some things never will, just based on what they're doing, what kind of host hooks they have. They may just not run that way. And so being able to still containerize those and get the advantage of the additional tooling is great. And this gives you that knife for these types of use cases. So really cool piece of technology, really something to think about to help you understand containerization technologies a bit better. If you like what you saw here today, please like, subscribe, ask any questions you like in the comments. We've got more content coming soon. Until then, Curious Tech out.